Hello students, welcome to Engineers Academy. Today we are going to solve this problem, and the problem says that the boom OA carries a load P and is supported by two cables is shown. Knowing that the tension in cable AB is 183 pounds and that the resultant of the load P and of the forces exerted at A by two cables must be directed along OA, determine the tension in cable AC. So this boom OA is supported by these two cables and it is carrying this load P, and we are given the tension in cable AB, the magnitude of the tension in cable AB, which has a magnitude of 183 pounds, and we are asked to find the tension in cable AC, the magnitude of the tension in cable AC, but with the condition that the resultant is acting along this OA line. So this means that the resultant is acting along the x-axis. This means that the y and z component of the resultant are 0. So let me write the resultant. If we write the resultant as a Cartesian vector, let me write it as rxi plus ryj plus rzk. And if the resultant is acting along this OA line, the resultant must be acting in the negative x, since we can see that if this is the tension in cable AC, so it will have one component in this direction, it will have one component in the negative x, and it will have one component in the positive y. And similarly, the tension in cable AB will have one component in this direction, since it is going away from this point A in this direction. It will have one component in the y direction and it will have one component in this direction. So since both of these tensions have the component in the negative x, so they will sum up and will give us the x component of the resultant. Or we can say that those two components of the tension which are acting along the negative x-axis will give us the resultant. Since the problem says that the resultant is only acting along this OA boom, and so the ry component of the resultant is 0 and the rz component of the resultant is 0. So let me write that rx will remain, ry is 0 and rz is 0. So this is 0k. And now let me represent the tension in cable AC and cable AB. So let's say that this is the tension in cable AC and this will be the tension in cable AB. And if I represent the components of both of these tensions, so TAC will have one component in the negative Z. This will be TAC Z component. Similarly, this will have one component in the negative X, since from A this TAC is going inwards, and that is away from the positive x-axis, right? We can see that this TAC is going in this direction, so the x component will be in this direction, since from point A it is going inwards, that is towards point C. So this will be the x component of TAC. So this is TAC x component, and similarly we will have the y component like this, parallel to the y-axis. This will be TACY, TACY. TAB will have the z component in this direction, since the tension in AB is going away from point A in the positive z direction. So the z component will be in this direction, the y component will be in the upward direction, and the x component will be in this direction. So this will be TABZ. We will have the x component in this direction, TABX, and we will have one component in the positive y. So this will be TABY. So again, this is TABX, this is in the negative x, this is TABY, and this is TABZ. Now since the black one is the resultant, and the problem says that the resultant is directed along line OA, so the ry component of the resultant is 0 and the rz component of the resultant is 0. So this means that if we sum up the z components, if we add up the z component of this and this, so they will cancel out each other. So this means that TACZ and TABZ, they are equal. From our observation, we can say if the resultant is acting along the negative x, that is along the boom, so we can say that TAB, the z component of TAB will be equal to the z component of TAC. And similarly, since the resultant is acting along OA, so we can say that the sum of the y components TABY and TACY will be equal to the P force, that is the load which the boom is carrying. Since these two components will balance the load in order to keep the boom in its current position, that is along the x-axis. So we can say that, let's say this is equation 1. And we can say that TABY plus TACY, that must be equal to that load which the boom is carrying. Let's say this is equation 2. And similarly, the resultant will be equal to the sum of both of these. The x components will give us the resultant magnitude. If the problem asks us to find the resultant magnitude, then we can say that the resultant will be equal to, the resultant magnitude will be equal to TAB x plus TACY. And since TABX and TACX both are acting in the negative x, we will get the resultant, and the resultant will be directed along the negative x-axis, as I have discussed already in the start of the problem. So now I need to find TAB, Cartesian vector. So TAB will be equal to its magnitude. Its magnitude is 183 pounds times the unit vector from A to B. And we can say that 183 and the unit vector from A to B is the position vector from A to B divided by the magnitude of the position vector from A to B. So TAB, Cartesian vector, is equal to 183 pounds multiplied by the position vector from A to B. Now we can find the position vector very easily. From A, we need to travel 42 inches in the negative x, then 29 inches in the positive y, and then 24 inches in the positive z. So we will reach this point B from point A when we travel along the x, y, and z axis like this. So I can write that we need to travel 48 inches in the negative x, that is in the negative I, then this 48 inches, then we need to travel 29 inches in the positive j, and then we need to travel this 24 inches in the positive z, so plus 24k, and then we need to find the magnitude. We can find the magnitude like this. This will be 48 square plus 29 square plus 24 square under the square root. So let's find this magnitude. This will be 48 square plus 29 square plus 24 square. This gives me 61. The magnitude is 61. And now we can divide this magnitude by 61. Let me erase all these. The magnitude is now 61. And now we need to multiply this 183 divided by 61 with each component of the position vector from A to B. So we will be able to find the Cartesian vector representation of the tension in cable AB. So 183 divided by 61, this is 3, right? So 183, let me write it like this: 183 divided by 61 multiplied by minus 48, this gives me minus 144i. I need to multiply this fraction with all the components. So multiply by 29, this gives us plus 87j, multiply by 24, so plus 72k. So now this is the x component, this is the x component, this is the y component, this is the z component of the tension in cable AB. Similarly, we need to find the Cartesian vector representation of the tension in cable AC by applying the same method. So let's find TAC, Cartesian vector. This will be equal to its magnitude. The magnitude is not known. Let's say that the magnitude is TAC times the unit vector from A to C. So this will be TAC magnitude, and the unit vector from A to C is the position vector from A to C divided by the magnitude of that position vector. So this is TAC magnitude, and now we need to find the position vector from A to C. Again, we need to travel from A along the x, y and z axis in any order to reach that point C. So from A we need to travel 48 inches in the negative x, then we need to travel 36 inches, or we can say we need to travel 48 inches in the negative x, then we need to travel 25 inches in the positive y, and then we need to travel 36 inches in the negative z. This distance is in the negative z. So we will reach this point C from point A. So we can write that we need to travel 48 inches in the negative I, then we need to travel this 25 inches in the positive j, and then we need to travel this 36 inches in the negative z. So minus 36k. Now we can find the magnitude. The magnitude will be 48 square plus 25 square plus 36 square under the square root. So this will be 48 square plus 25 square plus 36 square. This gives us 65. Now we can say that, let me erase this and let me replace this with 65. So this is 65. Now I need to divide all these components by this 65 and need to multiply it with TAC. So we can write this as minus 48 divided by 65 multiplied by TAC I plus 25 divided by 65 into TAC j minus 36 divided by 65 into TAC k. This is equal to TAC Cartesian vector. Now, as per our discussion, equation 1, the z components, the z component of TAB and the z component of TAC, they will be equal if the resultant is acting along this boom OE. We need to write this equal to this. So this will be, we can say, 36 divided by 65 TAC equals to 72. So now we can say that TAC is equal to, if we cross multiply, so this will be 72 multiplied by 65 divided by 36. So TAC magnitude is 72 multiplied 65 divided by 36. This gives us 130, and this will be in pounds. Since this is in pounds and this is also in pounds, since the magnitude of TAB is given in pounds. So TAC magnitude, the tension in cable AC is 130 pounds if the resultant is directed along that line OA. So this is the required solution. But if in the problem, if we were asked to find the magnitude of the force P, the load which the boom is carrying, the load which the boom is carrying at A. So if we were asked to find that, we can find that, we can add the Y components and we will get the magnitude of that force P. So now let's find that magnitude of force P, that load which the boom is carrying. So P will be equal to the sum of the Y components. So the sum of the magnitude of the Y components. So this is 87 plus this. So 87 plus 25 divided by 65 into the magnitude of TAC, which is now known, which is 130. So 87 plus 25 divided by 65 multiplied by 130. So this gives us 137. So P is 137 pounds. And similarly, if we were asked to find the resultant, then using the equation 3 we will be able to find the resultant, and that this equation will also give us the magnitude of the resultant. So the resultant magnitude, these are all the magnitudes, right? They doesn't tell us the direction, right? This is the magnitude of TAC as well. So now the resultant is adding both the x components. So now the x component of TAB is 144 and the x component is this 144 plus 48 divided by 65 into TAC, which is 130. So 144 plus 48 divided by 65 multiplied by 130. So this gives us 240. So the resultant magnitude is 240 pound. Now we know the TAC Cartesian vector. We know this TAC Cartesian vector. If we plug in this 130 pound value in all these, we will be able to find the Cartesian vector representation of T and C, and we will be able to find all the components of TAC along the x, y and z. And as we know that this resultant is acting along OA, and from all the discussion we know that the resultant is acting in the negative x. So we can write that the resultant vector is 240 pounds in the negative I. Its j component is 0 and its k component is 0. This is given in the problem statement. And similarly, we know that that load P is acting in the downward direction, that is in the negative y. So if we were asked to write this load P as a Cartesian vector, then its x component is 0, its I component is 0, its j component is, the magnitude is 137 and it is acting in the downward direction, that is in the negative j, and its k component is 0 as well. So this is the Cartesian vector representation of that load P. So this is the solution of this particular problem. I hope all this discussion and solution will help you in your understanding of this problem. Do subscribe Engineers Academy if it helps in your learning.